Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 1 on functions.
Welcome to Chapter 1. Every story begins with a cast of characters. In this story of calculus, our characters are functions, and the plot revolves around how these functions interact with each other and what characterizes them, from the local workings of their inner behaviors to the global sweep of their asymptotics. This lesson and this course begin with functions.
Calculus is all about functions, and indeed, that is where this course begins. Now, you're probably used to thinking about functions in terms of their graphs that pair x with f of x for a function f. One can also take a more mechanistic view, where x is considered as an input to f, and f of x is considered as the output. Indeed, visualizing this as a machine is extremely helpful, where one feeds x into f and receives as an output f of x. With this in mind, certain terminology about functions becomes natural. For example, the domain of a function f consists of all possible inputs, all the things you might put into the function. The range of a function f consists of all possible outputs, things you might receive from f. Now, this is single variable calculus, and because of that, our domains and our ranges are going to be relatively simple. They are going to consist of either the real number line or certain subintervals thereof. Certain operations on functions become critical. Perhaps the most important is that of composition. F composed with g. This is the function that takes as its input x and returns its output, denoted f composed with g of x, and that is g of x fed into the function f. We say f of g of x. One can visualize this as chaining together the functions f and g in the proper order. G comes first, and then f. For example, if one considers the function square root of 1 minus x squared, how can one decompose this into the composition of f and g? Well, f, in this case, would be the function that is on the outside, or that is done last. This is the square root function. G, that which comes first, is what is on the inside of the square root function, namely g of x equals 1 minus x squared. One additional important operation on functions is that of inverse. The inverse of a function f is denoted f with a superscript -1. Don't let that fool you. That does not mean you take the reciprocal of f of x. Indeed, f inverse of x is defined as that function which takes as its input x and returns as an output f inverse of x, such that if one composes with f, one gets back the original value of x for all such x. And now, one can also run this in reverse. If you do f first and then f inverse, one again obtains x. That means that intuitively, f inverse is the machine that undoes whatever f does. Let's look at a specific example where we take as f the function x cubed. What would the inverse of this be? Well, it has to be a function that undoes whatever x cubed does. This is, as you may have guessed, x to the 1/3 power, or the cube root of x. Now, there are several ways to see why this is right. One is that in taking the inverse, we are reversing the role of the input and the output. Or geometrically, we are flipping the graph of this function along the diagonal line where the input and the output are equal. Of course, we can also think in terms of what the inverse has to satisfy. If we do x cubed and then take its cube root, we get x. Or the other way around, if we take the cube root of x and cube it, we get x. Certain classes of functions wind up being extremely important throughout calculus. Perhaps the simplest such class is that of the polynomials. That is, functions of the form a constant plus a constant times x plus a constant times x squared, all the way up to some finite degree, constant times x to the n. That largest power of x is called the degree. There is a summation notation that makes writing out polynomials very simple. We use the Greek capital sigma and write a polynomial as the sum, sigma, as k goes from 0 to n of c sub k times x to the k. Here, the c k's are coefficients, or constants. Another class of commonly observed functions are the rational functions. These are functions of the form p of x over q of x, where p and q are polynomials. Simple examples like 3x minus 1 over x squared plus x minus 6 are very common throughout mathematics and its applications. Rational functions are very nice to work with. You do, however, have to be careful of what happens in the denominator when you try to plug in a value of x that evaluates the denominator to 0. Your function is not necessarily well defined at such a point. Other powers besides integer powers are important and prevalent. I'm guessing that you all know what x to the 0 is. That is, of course, equal to 1. What is x to the minus 1/2? Recall that fractional powers connote roots, and negative powers mean that you take the reciprocal, so that x to the negative 1/2 is 1 over the square root of x. And what is x to the 22/7? Well, break this up into pieces. First, we take x to the 22nd power, and then we take the 7th root of x. Lastly, what is x to the pi? Well, we're not going to answer that quite yet, but you may have a guess, especially considering the fact that there are rational numbers that are very close to the irrational number pi.